Hello students, welcome back to our physics lesson. In our previous lesson, we learned that spectroscopy is the study of interaction between matter and electromagnetic radiation. It involves the study of both emission spectra and absorption spectra. We have already studied emission spectra, which may appear as line spectra, band spectra, or continuous spectra. Today, we shall focus on absorption spectra. So what exactly is an absorption spectrum? An absorption spectrum is produced when light from a source passes through a material, such as cool gas, and some of the light is absorbed before reaching an observer. To understand this better, imagine shining white light through a tube containing a cool gas. White light contains all colors, which means it contains many different wavelengths. As light passes through the gas, the atom of the gas absorbs certain wavelength of light. The absorbed wavelengths disappear from the continuous spectrum and appear as dark lines. This pattern of colored light crossed by dark lines is called an absorption spectrum. Now let's look at line absorption spectra. A line absorption spectrum is obtained when white light passes through a cooler gas or vapor. The interesting thing is that the dark lines appear at exactly the same wavelength as the bright lines seen in the emission spectrum of that gas. This means that the absorption spectrum and emission spectrum of an element are closely related or perhaps the same. The difference is that in an emission spectrum, we see bright lines on a dark background. In an absorption spectrum, we see dark lines on a bright background. You can think of them as opposites of each other. But why do these dark lines appear? The answer lies in the energy level of electrons within atoms. Electrons can only occupy certain energy levels. When light passes through the gas, electrons absorb photons whose energies exactly matches the gap between these energy levels. The electrons become excited and move to higher energy levels. Almost immediately, they return to lower energy levels and re-emit the absorbed energy. However, the re-emitted light travels in random direction rather than continuing along the original path of the beam. As a result, less light of those wavelengths reaches the observer, causing dark lines to appear in the spectrum. Scientists measure absorption spectra using an instrument called spectrometer. A beam of radiation is directed through a sample, and the intensity of the transmitted light is measured. The results are usually plotted on a graph with wavelengths on the horizontal axis and absorbance on the vertical axis. One of the most famous examples of absorption spectra is the Fraunhofer's lines. These are dark lines observed in the sun spectrum. Scientists later discovered that these lines are produced when elements in the cooler outer layer of the sun absorb specific wavelengths of light coming from the hotter interior. The study of Fraunhofer lines allows scientists to determine the chemical composition of the sun. In fact, the element helium was first discovered in the sun through its spectral lines before it was ever found on Earth. Absorption spectra have many practical applications. They help scientists identify elements and compounds, study stars and galaxies, monitor environmental pollutants, and analyze substances in laboratories. Before we end this lesson, remember this important fact. The dark lines in an absorption spectrum occurs at exactly the same wavelength as the bright lines in the emission spectrum of the same element. This is because atom absorbs and emits energy at specific wavelengths, determined by their electron energy levels. Thank you for watching. Share your thoughts with me. Don't forget to like, share, and subscribe. And I'll see you in our next physics lesson, photoelectric effects.